All right, so today we're diving into a really foundational paper, one that introduced, well, a totally new way to think about training generative models in deep learning.
Yeah, it's fascinating. Think back to maybe the early 2010s.
Mhm.
Deep learning was crushing it,
Hmm,
especially with discriminative models, right?
exactly, like classifying images, is this a cat or a dog, that kind of thing. Networks got incredibly good at telling things apart.
But getting a network to create a new cat picture
Yeah.
or, generate any kind of new data that looked real.
That was much, much harder, a really tough nut to crack back then.
And it's worth digging into why it was so hard. The standard ways of building these generative models, they just kept hitting these major roadblocks.
Roadblocks like the math, basically.
Pretty much. You had these incredibly complex probability calculations you needed to approximate for training. Think maximum likelihood estimation.
Right, figuring out the probability of your entire data set given your model.
Exactly. And for deep, complex models, that often became, well, mathematically intractable, just impossible to compute directly.
And it wasn't just the core probability math, right? It was also hard to use the same tools that work so well for classification.
Yeah, things like those piecewise linear units, which were great in discriminative nets, were tricky to apply effectively in a generative context.
Well, the discriminative side was happily using backpropagation, dropout, things that were relatively, straightforward to implement.
Meanwhile, generative models were wrestling with other issues too, like Markov chain Monte Carlo methods in Boltzmann machines. They could be incredibly slow to mix.
Meaning slow to explore all the possibilities and give you good samples.
Right. Or you have things like the partition function problem, this normalization constant that's just notoriously difficult to compute.
It sounds like a real mess. Lots of different problems depending on the approach.
Definitely. Even methods that tried to use backprop, like generative stochastic networks or GSNs, still needed these Markov chains just to get samples out of the trained model. Kind of clunky.
And other ideas like score matching or noise contrastive estimation.
They had their own hurdles. They often required you to actually write down an explicit formula for the probability density the model represented.
Which, for a complex deep neural network, is basically impossible.
Precisely. So it felt like generative models were kind of stuck, hitting these computational walls.
Okay, so the stage is set. Generative modeling is hard, and then comes this paper we're looking at today.
That's right. Generative Adversarial Nets by Ian Goodfellow and his colleagues.
And our mission for this deep dive is to really get under the hood of this framework, understand how it works through this adversarial process, what its potential seem to be, and its challenges, based just on what this original paper laid out.
And the core idea is just elegant. Instead of one big hard math problem, let's set up a game.
A game between two neural networks.
Exactly. The paper used this great analogy. Think of one network as a team of counterfeiters. That's the generator, or G.
Okay, counterfeiters, what do they do?
Their job is to make fake money, or in this case, fake data samples that look absolutely real. They start with just random noise, like a blank slate.
And they transform that noise into, say, a fake image.
Precisely. Trying to make it look just like the real images from your training data.
Okay, so counterfeiters. Who are they playing against?
The police. That's the second network. The discriminator, or D.
Makes sense. And the discriminator's job.
Its job is to look at a sample, could be real money, could be fake money from the generator, and decide, is this authentic or is it a counterfeit?
So one network makes fakes, the other tries to spot them. A competition.
Exactly. The generator, G, is constantly trying to get better at fooling the discriminator, D. It wants D to make mistakes and classify its fakes as real.
While the discriminator D is trying to get better at not being fooled, it wants to correctly identify the real stuff as real and the fake stuff as fake.
And this whole competition is formalized mathematically. It's a two-player minimax game.
Minimax, meaning one player tries to minimize something, the other tries to maximize it.
Spot on. There's a value function, let's call it VG, D. The discriminator, D, wants to maximize this value function, which essentially measures how well it's classifying both real and fake samples.
And the generator, G, wants to minimize that same function, specifically the part that relates to D catching its fakes. It wants D to fail.
That's the game. And the amazing theoretical insight is what happens when this game reaches its equilibrium.
Assuming both players, G and D, are powerful enough, like perfect counterfeiters and perfect police.
Well, if they have enough capacity, yes. The theory says the game converges when the generator gets so good that its generated data distribution, let's call it PG, becomes identical to the real data distribution, P data.
So G learns to make perfect fakes.
Essentially, yes. And at that exact point, the discriminator is completely stumped. It can no longer tell the difference between real and fake.
So its output is just random guessing.
Exactly. The optimal discriminator, D, will output 12 for every input. It's basically saying 50-50 chances is real, I have no clue.
Wow. Okay, so the game's structure naturally pushes the generator towards matching the real data.
And the paper provides the mathematical proof for this, at least in a theoretical setting with infinite model capacity.
Yeah.
It shows the global optimum of this minimax game exists if and only if PG equals P data.
And at that point, the value of the game settles at a specific number.
Yes, -log 4. But more importantly, they connected this game objective to a known statistical measure.
Oh, right. The Jensen-Shannon divergence, JSD.
Exactly. That was a key theoretical contribution. They showed that for the optimal discriminator, the value function G is trying to minimize is directly related to the JSD between the real data distribution P data and the generator's distribution PG.
And JSD measures how different two distributions are.
Yes, and crucially, JSD is 0 only when the two distributions are identical.
So minimizing the GAN objective is essentially equivalent to minimizing the difference between the generated data distribution and the real data distribution.
Precisely. It provides this really strong theoretical justification for why this adversarial game should work. If D is always optimal, then updating G to minimize the value function forces PG towards P data.
Okay, that makes sense in theory, but how do you actually train this in the real world? You mentioned you can't just make D perfect at every step.
Right, that'd be computationally way too expensive. And, with limited data, D might just overfit and memorize the specific fakes G is making right now, rather than learning the general difference between real and fake.
So the practical solution is iterative.
Yes. Algorithm 1 in the paper describes it. You alternate, you take a few steps to optimize D, then one step to optimize G, then back to D, and so on.
How many steps for D versus G?
In their experiments, they actually use K1 for simplicity and speed. So one gradient step for D, then one gradient step for G.
Okay, one step each. D tries to get better at discriminating by ascending the gradient of the value function.
And G tries to get better at fooling D by descending the gradient, all using standard backpropagation.
Simple enough. But wasn't there a trick they mentioned for training G, especially early on?
Ah, yes, good point. The correct thing for G to do is minimize log 1. D. Remember, D outputs a probability, so the probability D thinks the fake sample G is real.
Okay.
But early in training, G is usually terrible. Its fakes look nothing like the real data. So D is very confident they're fake, meaning D is close to 0.
And log 1's something close to 0. It's close to log 1, which is 0. The gradient is tiny.
Exactly. The gradients for G become very small, very weak. G doesn't learn much. It's called the vanishing gradient problem in this context.
So what's the workaround?
Instead of minimizing log 1, D, Tengzizing, suggests maximizing log.
Maximizing the probability that D thinks the fake is real.
Right. This objective provides much stronger gradients for G early on when D is small. It gives G a better kickstart to start improving.
Does it change the final goal?
No. Crucially, both objectives have the same fixed point in theory. Maximizing log just behaves better early in training.
Clever. So they used standard neural networks for G and D, like MLPs?
Yep, multilayer perceptrons. They mentioned using things like real U and sigmoid activations in G, and interestingly, max-out activations in D. And dropout was used in D to help prevent overfitting.
And all trained with backprop. That sounds like a big advantage over some of the older methods.
Definitely. No need for complex sampling schemes just to get gradients.
Okay, so we have the theory, the practical algorithm. How did they actually show it worked? What were the experiments?
They tested it on standard image data sets of the time. MDS, handwritten digits, the Toronto Face Database, TFD, and CFAR10, small color images.
Right. And how do you evaluate a model like this? You said GANs don't give you an explicit probability number for a given sample.
Yeah, that's the tricky part. You can't just calculate the likelihood of your test set directly, which is a common metric for other generative models.
So what did they do?
They borrowed a technique used in other work, estimating the probability distribution of the generated samples using something called a Gaussian Parson window.
Parson window. That's like putting a little Gaussian blur around each generated sample and adding them up to estimate the density.
That's the basic idea, yeah. Once you have this estimated density from the generated samples, you can then calculate the average log likelihood of the real test data under this estimated density.
How reliable is that method?
Well, the paper itself notes its limitations. It can have high variance, the results can jump around a lot based on the specific samples generated, and it doesn't perform particularly well in high-dimensional spaces, like images often are.
But it was kind of the best they had at the time for a quantitative comparison.
Pretty much. They use cross-validation to set the width, the sigma parameter of those Gaussian windows, trying to be as fair as possible.
And what did those quantitative results show?
Looking at their Table 1, the log likelihood estimates they got on MNIST and TFD were reported as competitive with, or sometimes better than, other leading generative models of that era, like deep Boltzmann machines or stacked denoising autoencoders.
So quantitatively, it looked promising despite the metric's flaws.
Right. But maybe even more persuasive, I think, were the actual images they generated, shown in the figures.
The samples themselves?
Yeah. These weren't averages or reconstructions. They were just raw outputs from feeding random noise into the trained generator. And they looked pretty good for the time.
And they made a point of saying these weren't cherry-picked.
They did.
Yeah.
They also showed smooth transitions. If you slowly change the input noise vector, the output image changed smoothly too, suggesting the generator had learned a meaningful, continuous space of images.
Seeing is believing, I guess. Those samples likely made a big impact.
I think so. It was tangible proof of concept.
Okay, so based on all this, what did the paper list as the main advantages of this adversarial approach?
Several key things. Big one. No Markov chains needed, either for training or sampling. Just feed noise to G, get a sample. Simple.
Huge advantage over things like Boltzmann machines, then.
Absolutely. Second, only backpropagation is needed for training. Leverage all the existing deep learning infrastructure.
Also very practical.
Third, no complicated inference needed during learning. Fourth, flexibility. You can use lots of different kinds of differentiable functions for G and D.
Opens up architectural possibilities.
Right. Fifth, they argued genes could potentially represent very sharp distributions, even degenerate ones where all the probability is concentrated on a thin manifold, which some other methods struggled with.
Why is that important?
Some methods, especially those relying on MCMC, implicitly prefer blurrier distributions because it helps the Markov chain move around. Genes don't have that constraint.
Interesting. Any others?
A final, more speculative one. Maybe a statistical advantage because GDO doesn't learn directly from data examples, only from D's gradients. Kind of an indirect learning signal.
Okay, lots of potential upsides. What about the downsides? What challenges did they identify?
The main one ties back to evaluation. You don't get an explicit probability density function, PGX. You can sample from it, but you can't easily ask, what's the probability of this specific image X?
Which makes likelihood-based evaluation difficult, as we discussed.
Exactly. The other big challenge highlighted was training stability. D and G need to be well synchronized.
Synchronized.
Yeah, you can't let G get too far ahead of D. If G becomes too good too quickly, D doesn't provide useful gradients anymore. G might just find one or a few outputs that fool the current D really well and then collapse.
Collapse, meaning it only produces those few outputs.
Right. It stops exploring and generating variety.
Right.
The paper has this great name for it, the Helvetica scenario.
Yeah. Like everything just looks the same, like one boring font.
Exactly. G collapses to producing very few distinct, often uninteresting samples because it's easier than learning the full complexity of the data distribution once D falls behind. Keeping D strong enough to provide good feedback is crucial.
That makes sense. Maintaining that competitive balance is key. So finally, did they look ahead? What future work did they suggest?
Oh yeah, they laid out several interesting directions right there in the first paper.
Like what?
Conditional GANs were a big one. Generating an output conditioned on some input C, like generate an image of a 7 given the label 7. You just feed C into both G and D.
Seems like a natural extension.
Definitely. Also, learned approximate inference, training another network to try and map a generated sample back to the noise Z that created it.
Sort of reversing the generator?
Kinda. They also mentioned using GANs for structured prediction tasks, like modeling parts of data given other parts, and using the features learned by D for semi-supervised learning.
Using the discriminator's knowledge for other tasks.
Yeah, since D learns useful features to distinguish real from fake, maybe those features are helpful for classification when you only have a few labeled examples but lots of unlabeled ones.
Clever. Anything else?
Just the general point about improving training efficiency and stability, finding better ways to coordinate G and D, which obviously became a huge area of research later.
Wow. So a really groundbreaking paper. Let's try and sum it up.
Okay. At its core, it's this brilliant reframing of generative modeling. Not as direct probability density estimation, but as a game.
An adversarial game between a generator creating fakes and a discriminator spotting them.
And this framework managed to sidestep many of the really difficult computational hurdles, intractable likelihoods, slow Markov chains that were holding back earlier deep generative models.
And importantly, it showed right away that it could produce compelling samples, giving a glimpse of the potential for generating really realistic synthetic data.
Absolutely.
Yeah.
Understanding this GAN framework, this adversarial principle, is just fundamental if you want to follow the progress in generative AI over the last decade. Images, text, audio, you name it.
It really changed the game. So here's something to think about, building on our discussion. The paper establishes a powerful framework, but also highlighted the lack of an explicit probability density PGX and the issues with evaluation metrics like pars and windows.
Right, the evaluation challenge.
So the question for you, the listener, is, if looking at samples is subjective and likelihood metrics are often unavailable or flawed for models like GANs, how should we really evaluate if a generative model is good? Does this adversarial setup itself suggest new ways to evaluate generation, maybe ways that don't rely on explicit probabilities at all? What might those look like?
That's a deep question. What does good even mean if not likelihood? Something to mull over.